Welcome back to ECE 220. Announcements. Passport assignment is due on, what day is that? Saturday? Saturday, I should list that, the 31st of August, the last day of August, as is homework assignment number 0. And homework number 0 is experimental in the sense of you're trying to get familiar with mastering. It won't count towards your grade. So you can play with that as you like. But homework number 1 is due on Tuesday, the day you return from our break. Unfortunately, homework number 1 is not yet available to you. That needs to be created, and I'll try to get that done as soon as possible. But just note that that is due on Tuesday. And all the subsequent Tuesdays of the semester will have a homework due. So now this Tuesday you didn't have a homework due, but all the following Tuesdays you will for this class. Today we want to get into passive sign convention. And after defining that, we will look at the meaning of the polarity of power, P of T. If it's greater than 0, then that, using the passive sign convention, that element will be absorbing power. If P of T is negative, then that particular element is supplying power to the rest of the system, whatever our system consists of. Then after we've learned all of that, learned in quotes, I'll give you a quiz. And the quiz is concerned with the passive sign convention, making sure you understand that, what that means, and using it to tell us whether we are consuming or delivering power. Once you have the passive sign convention established, then you can figure out, is this particular circuit element consuming or delivering power? We'll then distinguish between power. I've labeled little p of t. That could be instantaneous, but we may want to just look at that over an average or over a particular time interval and establish an average. If we're in this class, actually that instantaneous, since all of our stuff is DC or constant, that instantaneous power will be the same as average power. But in the next class, you definitely need to know the difference. But a lot of times it's more convenient to just refer to or work with the average power. We know how to get energy from power. We'll just review that. And then here's a point that I hope that you don't struggle with. It's the labeling. It's like, I don't know if this is positive or negative. What should I label it? Don't get hung up on the labels that you're assigning to your polarities of power or to the directions of the currents. That's what I'm hoping to make clear in that part of today's class, is the non-critical nature. It'll take care of itself. If you're applying the passive sign convention properly, it won't matter if you made your current go from left to right and somebody else defined a current from right to left. You'll get consistent answers. Not the same. One will be the negative of the other, but everything will work out if you work properly or apply the process consistently. And then the end of chapter 1 is power balance. So you need to be reading along. As of yesterday, about 2/3 of you, I think, had access to the textbook. So the other third needs to get started. Passive sign convention. Where did that come from? What? Why do we need to worry about the sign convention? And maybe we can relate that to yesterday's class. How many went home and had to look at their power bill? Did anyone look at their power bill? You didn't get excited? No, you probably didn't get excited about the power bill, but after seeing how much a lightning bolt might cost you, what did we say that was going to be? $10,000. Hopefully you're not paying that monthly in your power bill. And maybe power bill is a little misleading. You're really paying for energy, aren't you? You're consuming power, and that's kind of what you're demanding to keep things running. But the power you're utilizing over an interval of time is the energy you're consuming, and that's what you're paying for. If you now said, okay, my power bill is $100 a month, then how many months would that lightning bolt's energy provide for your consumption? That was 10 to the fourth. You now have 10 to the 2 that you're using every month. So you're left with 10 to the 2, or 100 months. If you could somehow capture the energy content in that lightning bolt, you would have 100 months worth of power. 100 months of energy with which you would consume via power. Or if that doesn't resonate, you could say, oh, we could power 100 homes in a month with that lightning bolt that we worked on in class yesterday. Just to give you a feel for, I don't know, gigajoules, terajoules, who really... Well, now you maybe have a better feel. Oh, that lightning bolt, 100 months of my... And what's that? How much is 100 months? Let's see, divide it by 12, 8 goes into 100, or 12 goes into 100 8 times with a little bit more. 8 times 12 is 96, so we left with 4 months extra. 8 1/3 years worth of energy that you could get from that lightning bolt. 8 1/3 years. 8 years, that's high school and college, right? So you could supply your energy needs through high school and college with one lightning bolt. Just putting things into perspective. And you don't get off free, do you? Usually. The power company wants to make sure and charge you. That's why this passive sign convention is so important. They want to know, how much am I giving you, how much am I supplying you, and how much are you demanding or consuming. That's what we are going to be keeping track of. Plus, power is important because that may be a nicer variable to keep track of. Meaning, if the power company said, oh, I'm going to charge you based on voltage, you could kind of rig the system. You could say, oh, I'm going to drive my voltage, I'm going to set it really low and make my current really big. Well, they're charging me based on voltage. I'm not going to pay much. Well, it's the product of voltage and current that you are using to assess your power demands. So that's why we're having to keep track of all of these different variables. In this sense, power, or the amount of power over a given time, energy, is now what you're having to pay for. Let's now establish this passive sign convention. I've now labeled a two-terminal device, or a two-terminal element. I've assigned a current going from left to right, and I've just said the polarity markings on that two-terminal element are on the left is plus and on the right is minus. Here's the passive sign convention. If the current that you've drawn, the current arrow, enters, that's what I'm going to try to write here. If that enters the positive voltage label that I've just assigned to that element before passing through the element, then the power formula is written with a positive sign. or P of t is now going to be, and a lot of times we don't even put that in there, V of t times I of t. Did anyone, are you helped by me giving you these notes prior to class? Is that helpful? So I'm kind of zipping through this if you're trying to frantically write all of this down. But hopefully you'll have the notes after class. You have some incomplete notes before class. We'll see how long that lasts. But is it clear what I'm trying to say? If the current arrow goes into the positive label that you have on your element before the arrow goes through the element, then you say, oh, P of t of that circuit element is just going to be written as V times I. You can contrast that now with the opposite picture. Pardon? So here is what we had before. We have our two-terminal element, positive to negative, left to right, arrow going into the positive label before the current or the arrow that you've drawn goes through the element itself. That is now written as P of t is VI. The other case, suppose now we have the current, again going from left to right, but now we've labeled our the voltage polarity on our two-terminal element differently. Now it's negative on the left and positive on the right. If the current arrow goes through the element before it touches or gets to the positive voltage label, hopefully you can see the distinction or the difference. If you have this case, then in the power formula, and this is just a power formula, in the power formula we now need to include a negative sign. We have minus V of t, I of t. The question was, if it's not labeled, we just assume, I would say, let's back up. If it's not labeled, we need to label it. We need to label it so that we know what's going on. So the very first thing that you'll probably be doing in these circuit analysis problems is putting labels on your circuit. And later we'll see that how you label it is not critical, but you just have to stick with the labels. Once you've labeled it, now you work the problem. You can't be changing signs and doing things crazy after you've labeled it. So the critical thing is label your circuit elements either this way, positive to negative with the current going from left to right, or this way. It doesn't matter. But once somebody says, what's the power associated with that circuit element, it does matter how you've labeled it. In the first case, the arrow goes into the positive voltage terminal before going through the element. Its P is VI. If it's the other, if the current goes through the element before it touches the positive polarity label, then you put in P is equal to minus VI, irrespective of what V and I are actually valued as. V could be positive, V could be negative. That's not being discussed right now. We're just trying to establish this formula consistent with the labels. And we call that the passive sign convention. And now let's see what that means. The meaning of of power's polarity, or what are we implying by this passive sign convention? The circuit element is absorbing power from the rest of the circuit when P of t is positive. If P of t is 0, it's not absorbing or supplying, so we'll just look at positive and negative. So P of t is positive. And here, key word is the circuit element is absorbing power. Now, I may say that many different ways. Other phrasing, they mean the same thing. The power is consumed by the element. That's another word that's consistent with absorbing. This two-terminal element is consuming power if P is positive. And P being positive is not the same from this formula. I'm distinguishing between that positive sign in front of V and I with P of t being positive. Is that clear? Whether P is positive is going to depend on what V and I are sign-wise. Another way that I might state this is power is dissipated by the element. If you're pushing a lot of current through a resistor, that resistor may get hot. It may even be too hot to touch. You may burn your finger. And you have to worry about power ratings on the resistor in terms of can they tolerate that much current. But you're obviously dissipating power through that resistor. It's giving off heat. The other case, the circuit element is providing, and in this case, there's our key word. The circuit element is providing power to the rest of the circuit when P of t is less than 0, or when P of t is negative.
So if you're like thinking about a light bulb, it being sensitive, it's consuming power, but it's giving off heat, or dissipating as well.
So the question is something about a light bulb. So if you have a light bulb, an incandescent bulb versus an LED, an incandescent bulb gives off more heat. But essentially, you, as an electrical engineer, you might view that light bulb as a resistor. It's now consuming or dissipating, or what was my other word that I used? Consuming, dissipating, or absorbing power. You're pulling power from the power company when you're lighting that bulb. You're consuming power. You're absorbing power. That's when P of t is greater than 0. In the other case, if it turns out after you've labeled your circuits, you've found the voltage across that two-terminal device, and you found its current, you form that product, and P of t is negative, you go, oh, this is actually supplying power to the rest of the circuit. And that two-terminal element might be a battery. And it's powering your circuit. So the circuit element, is providing power when P of t is less than 0. Another phrasing for that is the circuit element delivers power to the rest of the circuit. Or, and sometimes these notes are not complete, obviously, before. So let me, unfortunately for you, cut and paste. Another phrasing might be that the circuit element supplies power to the rest of the circuit. In a very general sense, power company is supplying us with power. We're consuming it. We're dissipating it. Everything in our house is basically acting like a light bulb. Relative to a light bulb, do you know what we are? What? I don't. All right. So how many calories do we normally consume, or do they say an average person might need to sustain their existence? 2,000 a day. If you work that out, calories are energy. So now you do all the conversions, you'll end up seeing that that corresponds to we as a person are basically like a 100-watt light bulb. Average, all the time, we're just a 100-watt light bulb. Which means when you have 100 students in a classroom, there's 100 100-watt light bulbs energized in that classroom, dissipating our heat, and it warms up the room, doesn't it? So we have several 100-watt bulbs all lit up in this classroom. 60, I don't remember the number, 70 in the class. But that's our power. So if you said, 100 watts for 24 hours, that's going to be 2,000 calories if you do all the conversions properly. So what can we take from that? Or what was I trying to make clear before? P of t equaling VI, which we would write down from our passive sign convention, could produce a positive value or a negative value, depending on what V and I actually are, the signs of those. Contrast that with, based on how we assigned the plus and the minus before on our two-terminal element, we need to, with the passive sign convention, say P of t is minus V of t I of t. Second case. Well, the end result, if you look at P of t, it might be positive or it might be negative. And it's an instantaneous. It could be varying, possibly. There's a distinction then between the formula P is equal to VI or P is equal to minus VI and what P actually ends up being. Is that clear? P could be positive or negative, and we now know if P is positive, what's happening? Are we positive? Yes, we're a 100-watt bulb, aren't we? What are we doing? We're dissipating power, 100 watts of that, all the time. So don't be negative. We aren't. We're positive, aren't we? If we're negative, what are we doing? We're eating. We're consuming. Consuming means we're burning it. If we ingest it, we're supplying our body. So if it's negative, then we are putting more energy into the system. All right, is this completely confusing? Now, I didn't label this because I didn't want you working the quiz before class. Here's our quiz to see if you're clear on what I'm trying to make the point of. Suppose now I give you a circuit element A, and I've labeled it now, or I will label it now. Let me go ahead and make this blue. Suppose now I say the current is there, and I'm going to make the polarity on my voltage that. I want you now to compute the power absorbed by each of these circuit elements, and there's a circuit element A, circuit element B, and a circuit element C. Here's what A looks like, and there's the I and the V for that. I want you to compute the power absorbed by each circuit element. There's the first one. B, the current I'm going to draw from left to right, and the voltage is minus to plus. And C is going to be plus V minus from left to right, and I. And I want you now to compute the power absorbed by each of those three cases, A, B, and C. And I'll give you a couple of minutes to do that. Yes. Is this being turned in? This is being turned into yourself. This is going to be in your notes. You're not going to be graded on this, but it's mainly meant to force you to think about what I've been rambling about this morning. Is it making sense? So if you want to put some pressure on yourself, view this as an exam, and you go, shoot, I have to answer this. Answer it as if you were taking an exam. View it seriously, because that's going to help you actually learn. Don't just say, oh, Tharp, he'll give me the answer in 5 minutes. That's not the point. Do you have an answer or some answers? Let's talk quickly about maybe one of those, or initially, let's just use the passive sign convention to find the formula that we need to be using. And that has to be done before you even worry about what the end result is, whether it's absorbed or supplied to the rest of the circuit, the power. And I ask you for supply or for absorbed. So if you ended up with negative power absorbed, what does that tell you? I'm absorbing minus 20 watts. What does that mean? That means I'm actually supplying the rest of the circuit with 20 watts. If I'm absorbing minus 20, then I'm actually supplying a plus 20 to the rest of the circuit. That's how you want to view these pluses and minuses on your end result. Passive sign convention, P of T for circuit A, what's that going to be? VI or minus VI? Everybody okay with this? VI? Circuit B, VI or minus VI? And circuit C? There's our formulas, and now you get to go with those formulas. The next thing that you would do, let's say now we said, okay, element A. You just told me that P of A is plus V of T, I of T. And in our case, V was given as 4, and I was given as minus 2. So we now have the power absorbed by that circuit element is minus 8 watts. or minus 8 watts is consumed. Depending on my mood or the phase of the moon, I don't know what I'm going to say. So hopefully these meanings will be consistent, but sometimes I might say consumed, sometimes I might say absorbed. Or what's another way of phrasing that? You could say the element is providing eight watts of power to the rest of the circuit. Or you could even say, oh, I don't like providing. You could say supplying. Is that clear? And now you can on your own work through the others. You should be able to. So there's a little space there. Power in general, or let's now define these two types of power. We have instantaneous power, where power is just the time rate of change of energy. And energy is in joules. Did anybody go home and eat an apple with a little bit different perspective? No? Gosh, you guys aren't doing your homework. Well, the critical homework is reading the book, right? Not so much apples and deer bounding across the interstate, etc. Joules per second, that's watts. And that's volts times current. That's instantaneous. And P of t could be fluctuating between plus and minus, depending on what V and I actually look like or are valued at sign-wise. Somebody else, the power company, might say, oh, your average power over the month was this. And then they just multiply it by so many days. Possibly. But you could now integrate that instantaneous power, divide it by the length of time you're integrating over, and that's now the average power over that time interval. And typically we label that with a capital P. And in our course, in ECE 220, we're really worrying mostly about DC, or direct current, systems, or circuits. In DC, direct current circuits, those are circuits that actually possess constant currents and constant voltages, meaning they're not changing with time. That's what we mean by them being constant. They're, as a function of time, they're constant. Under that scenario, the instantaneous power is in fact the average power. Wouldn't matter how long you integrated, as long as you divide it over that same length of time, your capital P is going to be equal to your little p, if P of t is associated with a direct current or a DC circuit. What about energy? How do we label this two-terminal element? Doesn't matter, does it? As long as once we've labeled it, we play with the labelings that we've assigned. So let's just say here's my I of t, and that's terminal 1, terminal 2, and here's my voltage. Is that formula correct? Is the power formula correct? Based on what? PSC, the power, what? Passive sign convention. So based on the passive sign convention, P of T is VI, and that's consumed by the circuit element. If it happened to end up being a negative value, that just means that that negative consumption really means it's supplying power to the rest of the circuit. Since P of T is the time rate of change of energy, then we can simply solve for the energy by multiplying by dt and integrating that side of the expression. Or Wt is now this integral of P of x dx over our time interval. And energy is going to give us joules. The power is watts, but watts are simply joules per second, and here the variable that we're integrating with respect to is time, and that has units of seconds. Our total energy could look, formula might look different depending on where somebody basically says you're drawing the time axis, or what you're considering to be the time axis. You might see a total energy formula written as W of T is integral from minus infinity to infinity of P of x dx. Or you might see it omega is equal to 0 to infinity P of x dx. Which of these lower limits is really going to be dependent on the problem statement or the problem that you're working on. If somebody gives you P of x from minus infinity to plus infinity and they say, what's the total energy? Then you need to integrate over minus infinity to plus infinity. If they say, oh, starting at t equals 0, this is what P of x looks like, total energy, then you just go from 0 up to infinity. That's the connection between power and energy. And if you're reading articles, and I may misspeak, they confuse power and energy all the time. They sort of view them the same. We say, oh, the power company. Well, they're really giving us energy, so you could think of them as the energy company. Or I might say the power bill. Well, it's really the energy bill that you're paying, but it's coming from the power company. But hopefully we can keep track of or keep straight the difference between power and energy. Labeling of voltage. We have two different choices. I could say, okay, here's what I'm going to say. That two-terminal element is 4 volts, left plus, right minus. That's equivalent to somebody else doing the following. What's an equivalent labeling of that two-terminal element? How could we label that a different way and it still be equivalent to what I've labeled on the left? What if I reversed the polarities? Now I have to change the sign on the voltage between those two polarity labels. Is that clear? Those two labelings are giving you exactly the same information. If somebody now says, oh, here's where my positive lead is and here's my negative lead, and I'm measuring with respect to those two leads, and they measure 4 volts, somebody actually said, oh no, I was using this as my positive lead and this was my negative lead, well, they're going to measure minus 4 volts. It's going to give you the same voltage relationship relative to that two-terminal device. Or reversing polarity negates the sign on the voltage value. If somebody now just flips the signs, the labels I should say, if somebody flips the labels on you, then you have to negate the sign on that value to get the same result. What about currents? Suppose we now had 2 amps going from left to right. What's an equivalent labeling of the right element? Is that clear? So now you could say, oh, I have electrons going from right to left. Well, that's equivalent to saying you have positive charge going from left to right of the same value. And we like to kind of not throw negative signs all over the place all the time. In electrical engineering, we like to work with positive charge. In physics, they may say, well, what are the electrons doing? Okay, well, that's now been labeled as a negative, and it can get confusing. So we just work with positive charge, flowing of positive charge. If I say my current is going from left to right and it's 2 amps, that's meaning a positive charge is going, what, 2 coulombs per second from left to right. So reversing the direction of the current negates the sign on the current's value. Let's look at an example. And now I was looking at this morning and I said this might get confusing because I've already had a circuit A or an element A. So let's redo this. Let me just say this is now element D and this one is element E. In case you're reading your notes and you go, wait a minute, he just said element A had this and now it's this. But hopefully you could see based on the context which one I was referring to. But to avoid that, let's now have 2 different elements, D and E. How are you going to label E to be consistent but opposite in sense of labels to the leftmost side? What would we do with the current? Now I have an arrow on the left going from left to right, low to big, or arrow pointing to the right. Here I would say, oh, I need my arrow pointing to the left. That means that I need minus 2 amps there. What about the voltage labels? Well, if I change those up, what's that say the numerical value needs to be between those labels? We need to reverse the sign or change the sign, so this is now minus 4 volts. Is that clear? Let's now look at what we have. So circuit D now. What's the passive sign convention tell us? What's the formula for P for the leftmost circuit element? Is it VI or minus VI? That's all I'm asking for passive sign convention. It's one of 2 possibilities. And this just depends on whether that current goes through the positive label before it goes through the rest of the circuit element. So in this case, it's going to be VI. And V is 4 and I is 2. So we have 8 watts is consumed or absorbed by that circuit element. What about circuit E? Based on the passive sign convention, what's the formula for power? P is VI, because the arrow is going into the plus before it goes through the element. So now circuit E says that this also is VI. In this case, what was V? -4. What was I? -2. 2 negatives make a positive. So now we have 8 watts is consumed by the circuit element, which is nice because now D, we tried to create it, or I gave you D, you tried to create circuit E to be consistent with circuit D. And they were, based on what we just performed via the analysis. We ended up with the exact same result. They both circuits, left circuit, right circuit, D and E, consumed the same amount of power. So it didn't matter how we labeled them, did it? If somebody labeled them one way, if you solve the problem properly, you'll get the same answer, effective answer, as somebody doing it the other way. Your answers may be the negative of each other, but you just have to now infer, oh, what direction was your voltage polarity, or what was the direction of your current? Oh, that's why our signs are different. But in this case, circuit D and circuit E are identical. What has to happen in a valid circuit? And here, if we do run out of time, this is the bookend, the bookends to chapter 1. The beginning of the chapter, they talk about a practical perspective, and there they might even be talking about light bulbs. Home appliances. All of these things have to be what? You're not going to get off by somehow saying, oh, I have a light bulb that the power company is not able to charge me for, and it's still really light or bright. No, they're going to capture that. Everything is going to balance. What you consume is what they supply. Here's a slightly different version of that. Suppose I now have a 2-terminal device A, a 2-terminal device B, C, I need to fit it on one screen, D, and E. What I hope to drive home is now if I say, okay, I'm going to analyze that circuit, or if I give this problem to you on an exam, you would need to make sure that if we're doing a power balance, that in fact all of the positive powers have to equal the negative powers. What's that mean? The power consumed has to equal the power supplied. If I now labeled this and said, oh, let's say that this voltage, let me just give it a value, is 12. Let's say B's voltage is left to right, 8. C's voltage, right to left, is 4. E's is minus 2 from top to bottom. D is right to left, 6. And we'll learn Kirchhoff's laws that will show us that those voltages are actually consistent or compatible. And maybe now I say, oh, this current in that top mesh is 4 amps, and this current is 2 amps. As an exercise, see if you can convince yourself that I've now assigned the proper polarities and currents to give a balanced power. So all of the pluses in power, the consumed powers, have to equal the supplied powers, all the negatives. That would be a goal of that exercise. We're out of time. Thank you. I'll see you tomorrow.